Okay, so last time we had introduced the concept of molarity, and we had gone through how to calculate the molarity of a solution, how to prepare a solution with a given molar concentration, and how to calculate molarity of solutions by dilution. And we had finished up some problems with C1 V1 equals C2 V2 and said this is only used when you're diluting. We do not use this for stoichiometry, which is what we're going to look at now. So molar concentrations are also useful in performing stoichiometric calculations for reactions in solution. And the solution reactions are usually titrations. This is what we did in lab last week. We have a reaction in solution. We have a known amount of titrant. That was the sodium hydroxide we measured out of the burette. We added it to a measured amount of solution that had an unknown concentration. That was our vinegar. And we used phenolphthalein as our indicator to change color to tell us when the reaction was done. And this works because phenolphthalein has a different color at different pH settings. So we can now use molarity as a conversion factor to do the stoichiometric math in these titration problems, just like we did in Chapter 3 when we were looking at stoichiometry using mass and molar mass as conversion. Since molarity is a two-part unit, it works nicely as a conversion factor. We know that we can take our molarity, uppercase M, and 0.5 molar is 0.5 moles per liter. Since 1 liter is 1,000 mils, it's okay for me to write 0.5 moles per 1,000 mils when I want to save a little time and avoid one conversion. And we can also turn this upside down just like we can with any factor, that 1 liter or 1,000 mils would be 0.5 moles. So let's look at the first problem, which is the simplest one. This is hydrochloric acid reacting with sodium hydroxide. We trade partners, do double replacement chemistry, and we get sodium hydroxide reacting to make sodium chloride and water. Now, when we look at this, the first thing we always do is balance the equation, and this equation is balanced as written. Now, we look at this problem. How many milliliters of 0.5 molar sodium hydroxide will be required to neutralize 25 mils of 1.75 molar HCl solution? I always say that it helps to write down all your factors. And I think in this chapter it helps even more than usual. So let's take the numbers and write them down away from the words. 0.500 moles of sodium hydroxide per 1 liter or per 1,000 milliliters, because I have information in milliliters and I want my answer in milliliters. I'll just convert to milliliters right here. And we know I have 1.75 moles of HCl per 1,000 mils of HCl. And I know that I have 25 milliliters of HCl. So that's all the numbers I was given in the problem. Now, I'm comparing sodium hydroxide and hydrochloric acid, so I want to look at my balanced equation and get the stoichiometric ratio. And when I look at this, this is balanced with all ones. So 1 mole of HCl reacts with 1 mole of sodium hydroxide. Now we can do the same kind of calculations we did back in Chapter 3, but since we're introducing molarity, this time we're going to be not using molar mass and not changing grams into moles, but we're going to change milliliters into moles. You remember in Chapter 3, we changed grams of A to moles of A, and then we went to moles of B using the ratio, and then grams of B using the molar mass. Now we're going to do a similar thing, but milliliters of A into moles of A to moles of B, and then moles of B to milliliters of B. So it's the same thing, but now instead of using molar mass, we're going to use molarity to make the first and the third conversion. This is where it's always hard to know how to show this, because some people say, well, start with what you're given. And some people don't understand which of these numbers that I'm given is the one I'm supposed to start with. I say when you're confused, start with what you want. And I'm going to show this example this way. Then I'll show it to start with what you're given way too, for those of you that don't like it backwards. But I think in these molarity problems especially, it helps to start with what you want. So what we want is milliliters of sodium hydroxide. This is the unit I want for my answer. So I'm going to start with that on top. 1,000 milliliters of sodium hydroxide contains 0.500 moles of sodium hydroxide. Now, I want to keep this unit and get rid of everything else. So I need to get rid of moles of sodium hydroxide. So I know that 1 mole of sodium hydroxide, so that'll cancel, uses 1 mole of HCl. So my moles of sodium hydroxide have canceled. Now I have 1.75 moles of HCl per 1,000 mils of HCl. So my moles of hydrochloric acid cancel. And I have 25 milliliters of HCl. So now my milliliters cancel, and I've gotten rid of everything except the unit I want. So sometimes I think this method is a really good way to do it, kind of going backwards if you're not sure what you need. And we get 87.5 milliliters of sodium hydroxide. Now, I know some of you were comfortable coming out of your intro classes and you say, well, what I was given is 25 milliliters of HCl. So now I'll change milliliters to moles. I have 1.75 moles of HCl is 1,000 mils. Now, mole to mole ratio, 1 mole of sodium hydroxide for 1 mole of HCl. So that cancels. And 0.5 moles of sodium hydroxide is 1,000 milliliters. So now I get the same answer. So if you look at these two, do you see that this is just going backwards? I just have everything exactly backwards. I'm still multiplying and dividing all the same numbers. So if you're not sure where to start, maybe this backwards idea will help you. Okay, go ahead and try this one on your whiteboards with your groups. The one on the bottom of page 419.